Hi everyone. Today's topic is thermal conductivity of a metal from Unit 2 Electron Theories of Materials. The definition for thermal conductivity of a metal is K, the thermal conductivity or coefficient of thermal conductivity of a metal can be defined as quantity of heat energy flowing through the metal per unit time through unit area of cross section per unit temperature gradient. The unit is watt, meter inverse, Kelvin inverse. Now, the thermal conductivity of the material is due to phonons and electrons. The lattice vibrations, that is, it is called as phonon, and the electrons present in the metal. So the total thermal conduction is based on the thermal conductivity of the electrons and the thermal conductivity of phonons. But in metals, since the topic is thermal conductivity of a metal, the due to the free electrons will be predominant. Now we are going to derive an expression for thermal conductivity of a metal. Consider a uniform metal rod. Let the two ends be A and B respectively. Let the end A is called as the hot end and end B is called as the cold end. The source of heat energy is present at the hot end and the temperature at end A is at higher level and the temperature at B is at the lower level. The direction of flow of heat is along positive x-axis. Let the length of the uniform metallic rod is 2 lambda. Let us consider the center part of the uniform metal rod as C. It lies exactly in the middle of the metal rod and equidistance of the two ends of the metal rod A and B. From A, C is at a distance of lambda. Similarly, from B, C is at a distance of lambda. Now, let N be the number of conduction electrons present in the metal rod per unit volume and V is called the thermal velocity of the electrons. Now, due to the movement of the electrons, there will be collision. Because of the collision, the electrons near the A end lose their kinetic energy and the electrons near the end B gain kinetic energy. The average kinetic energy of the electron is 3 by 2 kb T1. Similarly, the average kinetic energy of the electron at the end B is 3 by 2 kb T2. Number of electrons crossing per unit area per unit time of the metal rod from A and B is 1 by 6 NV. Here, the electrons can move in 6 directions: positive x-axis, positive y-axis, positive z-axis. Similarly, negative x-axis, negative y-axis and negative z-axis. But as per the diagram, the direction of flow of the energy is along the positive axis. Therefore, among these 6 directions, n number of electrons moving with the thermal velocity v will take up any one among these 6 directions. Therefore, the number of electrons crossing per unit area per unit time from A and B is 1 by 6 NV. Thus, the excess energy carried by the free electrons from A to B per unit area per unit time is 1 by 6 NV into 3 by 2 kB T1. This is the kinetic energy and this is the number of electrons moving along positive x-axis from A to B. Similarly, the deficient of energy, that is the deficit energy carried from B to A is 1 by 6 NV 3 by 2 kB T2, where T2 is the temperature at the end B. Therefore, net amount of heat energy transferred from A to B is 1 by 6 NV 3 by 2 kB T1 minus 1 by 6 NV 3 by 2 kB T2. 3 and 6 gets cancelled off and we have 2 here in the denominator. Similarly, we get 1 by 4 NV kB at both these sides. 1 by 4 NV kB. Similarly, here also 1 by 4 NV kB. Then T1 minus T2 is taken in the bracket. That is what given here. So this is the net amount of heat energy or net quantity of heat energy transferred from A to B per unit time across unit area of cross section. Now we know the definition for thermal conductivity is quantity of heat energy flowing per unit time across unit area of cross section per unit temperature gradient. That is, unit time denotes 1 second, unit area of cross section is taken as unity, 1 centimeter square, 1 millimeter square, 1 meter square. Therefore, these two becomes unity. And dt, temperature gradient, is difference in temperature with respect to difference in time. In the uniform metal rod, end A is with the temperature T1, end B is at the temperature T2. So the difference in the temperature dt is T1 minus T2. Then dx denotes the distance of T1 and T2. Therefore, this is equal to 2 lambda. Therefore, instead of dt, we are going to substitute T1 minus T2. Instead of dx, we are going to substitute 2 lambda. Therefore, K is equal to Q divided by T and A becomes 1. So, we are not going to take that. dt is T1 minus T2 divided by dx is 2 lambda. This is taken towards the numerator. So, this is the formula given here. K is equal to Q into 2 lambda by T1 minus T2. Now, substituting the equation, Q is equal to 1 by 4 NV kB T1 minus T2 in this equation Q. This equation for Q, we get 1 by 4 NV kB T1 minus T2 and then divided by T1 minus T2. That is, this is Q into 2 lambda by T1 minus T2. Here, T1 minus T2 get cancelled off and then here we have 2 and here we have 4. Therefore we get 1 by 2 NV, KB and lambda. So lambda is called as the mean free path of the electrons in the material. Therefore mean free path is distance travelled by the free electrons. We know distance travelled by relaxation time or the collision time. For a metal, the relaxation time and collision time are the same for the metal. Distance travelled by time taken is equal to the velocity. Therefore lambda can be replaced with velocity into time. So we are going to replace k is equal to half NV kb lambda with v tau. Lambda is replaced by v and tau as shown here. Kb is the Boltzmann constant. Here we have v and v. Therefore v into v is v square and it is consolidated as k is equal to half n v square kb tau. This is the required expression to determine thermal conductivity of a metal.